All right, so where were we? We learned about like cool aspects or ways that people are using computer science in social sciences and art and medicine and the hard sciences. We talked about protein folding, lunar landers, and things. There's one last area of computer science that's like taken over recently, and so I have to talk about cryptocurrency. I'm so sorry. So this is a topic that people feel very strongly about. I don't know if you guys do, shout out if you do. But we have somehow managed to combine cryptography and money, and then of course computer science has made some great strides in cryptography recently, and so that's why this is a thing. So let's talk about cryptocurrency. How do we have virtual money? All right, so I will focus on Bitcoin because that is still the most popular cryptocurrency these days. So what I'm about to say will apply to very similar to many other crypto coins that exist out there. A lot of them are based on Bitcoin. There are others that are based on other things like Ethereum, if you've heard of that. It's based on some other idea, but this more or less applies, all right? So Bitcoin is the most popular cryptocurrency, and so that's cryptography plus money, all right? So we'll try to talk about how that even works, okay? I am not going to go into too much depth because there's research papers on this, like the Bitcoin paper that released it all was a research paper, and it's very complicated. So I'll just talk about it at a high level with what you understand. But yeah, it's a type of money that's entirely electronic, and it uses cryptography, properties of encryption to make sure that nobody knows who's got what money. So it uses well, not really, but we learned about a very complicated kind of encryption with weird numbers, right? Weird prime numbers called RSA. Similar to that, something similar to that is what Bitcoin is used. What Bitcoin is using. Sorry. So yeah, just there's some weird properties of encryption that allow you to encrypt your own address. Okay, so let me try and explain that in a drawing, but I should say that it came out in 2009, so it's pretty old these days. Bitcoin came out in 2009, and it was released in a research paper just published on the internet by a person named Satoshi Nakamoto, which is not a real person's name. It's a fake name. It's a pseudonym. So we don't actually know who Satoshi Nakamoto is these days still. It's all up in the air. Who knows? But the idea of Bitcoin is you have a wallet. You have a Bitcoin wallet that holds your coins, and all a wallet is, you associate with your name. This is my wallet. It's really just a big long number, all right? It's encrypted, essentially. It's a big long number where people know how to get to you, and maybe you have 2 Bitcoins or something. So that's in your wallet. There's a way of tracking that. I'll explain it in a second. But it's all number-based and cryptography-based. And let's say that I want to give money to my cat. Let's say that he has his own Bitcoin wallet, which is just another big, long binary number, all right? It has to do with some properties of encryption as to how it's generated. And so Alonzo has 1 Bitcoin right now, and I want to give him 1 of mine. So there's some idea that Bitcoin gets behind and implements that allows me to say, hey, I want to send 1 Bitcoin to this Bitcoin address. This money goes here, and it will somehow move the money over to Alonzo's address, to Alonzo's account, and give him a Bitcoin and get rid of 1 of mine. And everybody agrees on that. Okay, so yeah, it has to do with encryption. So I'm able to spend my own money by having some sort of encrypted password to my account. Okay, that's kind of the idea. So we'll get into that in just a second. But yeah, everybody's wallet, we say, it's equivalent to the idea of an address. It's just a big number. Where does this number live on the internet? So every wallet is an address. Okay, I should say address, singular. Okay, and so there's other competitors to Bitcoin, like Litecoin or some other things. This is an old screenshot, but Bitcoin is still on top these days. All right. So yeah, do we own Bitcoin? Any of us? Are we into this at all? It's a little weird, but maybe we should have. I just checked the price right now before class, and it's up there, which is surprising. So let's talk about how Bitcoin works and how it makes sure that you don't spend too much of your own money. It makes sure you only spend as much money as you have, and it lets you give money to somebody else without anybody being able to track oh, this number was Lawton's Bitcoin number. All right, let's figure that out. It's called the blockchain. All right, that's where Bitcoin information is stored, and it's just a big place in cyberspace. All right, so what Bitcoin really is, it's like a file sharing service. It's really a peer-to-peer network. Do you remember what that means? It's just a bunch of computers connected to each other, all trying to agree on who has how much Bitcoin. That's pretty much what's going on. All right, so like there's a bunch of computers all connected all over the internet, and they are storing something called the blockchain. All right, so here let me draw an interconnection of computers. So all it is, it's a peer-to-peer network. It's a bunch of computers. Your computer could be on the Bitcoin network if you wanted it to be. It's got to download some stuff. All right, so they're all connected somehow in some topology. And like here on my laptop, I could connect to the Bitcoin network if I wanted to. All right, and start spending my own money. Okay, so that's kind of the idea. And it's powered by encryption again, right? So everybody's account number is, remember the public key, private key thing? So like if I own my account, that means I have a public key that I tell other people about. That's my Bitcoin address. That's how everybody knows I have this much Bitcoin. So my public key that I give to other people, that's my Bitcoin wallet address, and they can send money to that. All right, that's our account number. And then there's also a private key. That's kind of like the password to your account. You cannot use your account without its associated private key. Maybe I have that saved on my own computer. And then nobody else gets to spend my money with my public account because I have that private key tucked away in my pocket. Okay, that's the goal. All right, so that's kind of how accounts work. And then everybody agrees on how much money each account has. All right, and that has to do with the blockchain. So what the blockchain is, it's really just a big long file. All it is, it's like people call it a ledger. It's just a big long file that records every single transaction that has ever been made in the Bitcoin network. It's just a big long file. It's like, all right, person 1 spent this much money, sent this much Bitcoin to this account. Person 2 sent this much Bitcoin to this account. It's like everybody has a copy of this big long file that is the blockchain. You see how, like, if everybody agreed on what that file said, like, all right, yeah, person 1 did spend that money. If everybody agreed on the blockchain, like, I'll have a copy of it on my computer as well. You see how if everybody agreed, you could see how much money is in anybody's account just by running through all those transactions really quick inside of the computer. That's what's going to happen, all right? It's just a huge file that records every single transaction that's ever taken place since the beginning of time in Bitcoin land, all right? Which public keys have money, and like nobody is sharing their private keys, but that's how the money is getting moved around, all right? And so yeah, if you just go through it, start it from time 0 to today, you'll know exactly how much money each account has because like all the money being moved around is somewhere within there, okay? And so everybody on the Bitcoin network has a copy of that blockchain file, and they're all trying to agree on its contents, all right? That's what's going on. Does that make enough sense? Have we heard some of those words before maybe? That's the secret there. That's what's going on. And so, yeah, if I want to spend my own money, I have to, first of all, pick an account number to send it to, like another person's public key. And then I have to unlock my account with my private key to send it over, all right? So, yeah, whenever somebody spends their Bitcoins, they're going to use the encryption process. And then they're going to shout out that idea, like, I'm spending my money to everybody they're connected to. And so that's going to add a new piece of information to the end of the blockchain. And, like, these computers will tell the other computers that they're connected to about that transaction. That's how eventually everybody's going to know, like, okay, yeah, Lawton has spent his Bitcoin, okay? And they're all trying to agree on the contents, right, of that big, long file. Does that make enough sense for now? That's what's going on. That's the secret. And you may wonder, like, all right, how do you, like, is there a way to game the system, right? Because, like, I would like to have 1,000,000 Bitcoin just to myself, but I have to get all these computers to agree that I have 1,000,000 Bitcoin. That's the trick, right? How can I beat Bitcoin? Is there a way? Well, it goes by majority rule. That's the secret, all right? So if you're a bad person, you like to write, my account gets 1,000 Bitcoins to the end of the blockchain, right? You would want to do that, of course. You can try to do that, but it's not going to work because there's so many computers connected to Bitcoin, all right? Like, you got all these computers connected to Bitcoin, like, you'd have to take over the majority of the network to get them to agree, all right? It's majority rule. So greater than 50% of the computers all connected and storing their own version of the blockchain have to agree on a transaction in order for it to be set in stone. It'll be unrolled if somebody, like, tries to write this just to their laptops thing. Nobody's going to agree with that, okay? So if you're able to, like, maybe you controlled this much of the Bitcoin network, it's still not enough, right? you had a few billion computers, maybe you could take it over, but nobody has that much power. All right. So if you did, though, if you could take over every single computer right now, if you could hack them all connected to the Bitcoin network, you could then like have a majority. You could mess it up, but it's pretty hard to gain a majority because there's so many people connected, and that's kind of why people trust Bitcoin. Like, nobody's going to mess with my account because it would take computing power on the level of a few major countries. Okay, so that's the idea there. And many alternative coins have sadly met this fate. They have been ruined by somebody, like not enough people are on that network for that silly little tiny Bitcoin version, alternative Bitcoin. And so they're able to take over half the network, and then they print their own money at that point. All right, so that's how it works. Everybody's agreeing on the blockchain. There's some cool algorithms involved there, but as long as you can't take over half the network, everybody's going to feel safe. Their money is safe. Only normal transactions can go through and be written to that blockchain file. Okay. Any questions about that so far? Make enough sense? It was a little complicated if you've never heard of it before. You may wonder now, like, how did the first Bitcoins get made? Like, how do you write to the blockchain? Because nobody had any Bitcoins at the start of time. How did the first Bitcoins get made? And that has to do with the term mining. All right, so that's another way, other than spending money and like receiving it, to get Bitcoins. Okay, so that's something that used to be very lucrative. You buy a bunch of GPUs if you ever like built your own PC or something. GPUs used to be very expensive because everybody was trying to buy them all up to do Bitcoin mining. All right, so this is how money gets printed in the Bitcoin network. All right, so it's also an incentive because like it costs money and energy to put your computer on this network and to like save a big long file on your hard drive. So as an incentive for people to like stay on the Bitcoin network and make it large and have the strength in numbers, there's a little lottery that happens every time some transactions go through. All right, so what happens is everybody's working really hard to verify every transaction. Like, I'm spending my money. People are working hard to verify that, oh, yes, I had that money in my account. Everybody who does that, like, tells the Bitcoin network, yes, this is legit. Yes, this is legit. And one of those computers that checked that transaction gets a Bitcoin just generated out of thin air. That's what mining is all about. That's how money gets printed. Essentially, they're trying to compute a big long number. It's a math problem. Every computer is doing a math problem in the Bitcoin network to verify the transactions. Like, generate some number based on what transaction just is trying to take place, and then generate like in a way with encryption, put a certain number of zeros at the start of that verification cryptography thing. That's essentially what's happening inside of the Bitcoin network. It's like generate a number involving that last transaction in a way such that there are a bunch of zeros at the start. And like it's hard to do that and also verify it. And so it's just like a big long math problem that's going on inside the Bitcoin network. And whoever solves the math problem first, whichever computer is good enough and finds it first, the special number that verifies the transaction with a certain number of zeros at the start, then they get money. All right, and so that's how Bitcoin gets printed, and that's how the first people got their own Bitcoin. They just like verified the transaction at the beginning of time. Okay, and though you might think of inflation, if you've taken like an economics class, this might ruin itself if this keeps happening and like people keep making the same amount of Bitcoin. So the secret Satoshi Nakamoto like tried to solve this problem by making it so that when you mine Bitcoin at the start of Bitcoin's life, you like got a lot, but as time goes on, like nowadays, you make less Bitcoin every time you verify a transaction. And it's just going to become less and less and less up until like 2060 or something, at which point there will be no more incentive for mining. So like hopefully there's enough people on the network by then. You do make money to verify a transaction still, but there will be no more mining possible in like a few decades. All right, it's all going to run out. And so that's how, so that's the economic policy of Bitcoin, essentially. It's just like everybody's trying to solve a math problem to verify the most recent transactions, and whoever solves it first gets money. That's how mining works, right? So that's kind of cute. That's kind of fun. So that's an incentive for people to use their Bitcoin. So it's just a lottery, and it happens every couple transactions. They're all jumbled together. Just like one lucky person gets that new Bitcoin. Okay. Any questions about that? Do we know that before? Like that's what mining is? That's the word. I'm sure we've heard that word. Exactly, because more people want it when the price is higher. Yeah. Oh, nice. That's right. Hmm. Yeah, so it fluctuates. The people who want to mine, and so okay, yeah, it's fun to think about. Like, I don't actually remember, but I think some low level language to make things fast. I assume. Yeah, so they might. I can assume that one of the pieces of software on the Bitcoin network that runs it is made in C++, which is a language you learn in CSCI 40. So that might be an incentive to take CSCI 40. That's true. That's raising the popularity. Did you guys hear that? That was like some countries are looking to Bitcoin to stabilize their own currency. Yeah, which is very interesting. I forget all the which countries are doing it, but like there's like this is obviously an ethical dilemma, right? We should talk about it. Here's the prices of Bitcoin since I started teaching this class. By the way, the very first semester I taught it, it was at 11,000. Then it jumped up, and then like it just fluctuates down and up, down and up. And apparently it's the highest it's ever been right now since I took screenshots. So if I had bought Bitcoin a year ago in last fall, oh man, I would have made almost three times what I spent to buy it if I sold it now. Oh well, it's just gambling though. Well, we do need to talk about if this is okay or not, right? Because like the first people using Bitcoin, the whole point of Bitcoin is like nobody knows which account is one. It's just a number, right? It's not associated with a person until you cash out, until you translate your Bitcoin into dollars. Like somebody has to write down who did what there. But until you do that, Bitcoin can just be moved around between different random numbers essentially. Nobody knows who has what. So of course the first uses of Bitcoin were to buy drugs and to like do illegal things. So that's nice. And then of course you also don't need to pay taxes on any of that because like your government doesn't know like that this number is associated with your account. It's just Bitcoin flying around in cyberspace. You don't know which country it's associated with or anything like that. So governments don't like it because of that. You cannot like get somebody to pay taxes on Bitcoin. And then as you can see over time, it's just like going up and going back down. So there's no guarantees about the safety of Bitcoin. Like no government really, only a few small ones are backing it, and so like nobody has any trust in it. So it's not like staying at the same level like the U.S. dollar or some other currency. Okay, so we can ask our boys about this. Let's see. I should also say another bad thing. I forget. It takes a lot of energy to run the Bitcoin network. I forget if I didn't write that or not, but like the last time I read about it, it takes as much energy for all the computers on the Bitcoin network to like verify the transactions and to stay powered on as the country of Argentina uses. So it takes a lot of extra energy to just be on the Bitcoin network. And that is, I mean, that's not good for our planet. Okay, so that's a problem. So yeah, let's ask our boys at least. What would they maybe say about this stuff? I think like is it okay to use Bitcoin even if it's being used for bad things, even if like there are some downsides? There are also upsides. So I would say that Kant, he would probably, because he likes individual rights, he'd say like, you know what, I trust people should always be paying taxes. Like I trust people to do the right thing with their Bitcoin account, so I think that it should be okay for us to have it. But Kant is definitely living in a pie in the sky world. He has his rose-colored glasses on. I think that's what Kant would be. He would be pro-cryptocurrency, probably. And then a utilitarian like Mill would think about things maybe differently. He'd have like some sort of balance going on there. Like what weighs more? As far as a government is concerned, like the U.S., no government really likes cryptocurrency because it's hard to tax it, first of all. It's hard to tax it. It's very easy for, like, organized crime to move money around because, like, there's nothing, you don't have to, like, ship suitcases full of millions of dollars or anything, just, like, send virtual numbers around all over the place. And then just, like, the environmental cost, like I was saying, that takes up a lot of energy. So that's the cons of Bitcoin. What are the pros, though? It is good for individual freedom, I would say, to not be tracked, like who's spending what money. And so that's propping it up on the other side. That's the pro. Like, I'm sure you've bought things on Amazon, then saw or searched for something on Amazon, and then you see, like, on Instagram an ad for that thing you were looking at. Like, nobody can really track you in the Bitcoin network, and that's good for individual freedoms. Okay, so yeah, that's what's going on. Just like a bunch of computers working real hard, using a lot of energy to solve math problems to verify who's spending what. That's Bitcoin in a nutshell. Okay. Any other comments, questions about this? Because I like to every semester have a silly little in-class exercise that we pretend that we are humans on the Bitcoin network. So I'd like to introduce a new cryptocurrency with my cat as the mascot. We will call it Litcoin. All right. So we're going to have an exercise on the next slide, and we'll say that it's not worth very much, but I will give you a physical object if you do this. I have brought, here are your Litcoins. I will give you all a floppy disk. All right. Maybe you've never seen one of these before. You can take one of these home with you if you win the math problem challenge. All right. So the first person to come up on the board, I have 3 questions. The first person, like, you might as well focus on one because you gotta be fast. Right? So the first person to come up to the board and write the answer to one of the questions gets something. Right? That's what's happening under the hood. It's like computers solving math problems quickly. So I have some math problems on the next slide. Get ready, and then the first person to write the correct answer next to the number gets a Litcoin. Okay. So ready, set. Here are your 3 questions. All right. You probably want to focus on one of them, but the first people to solve these questions the fastest and to write their answer on the board gets to take home a souvenir. All right. And so this is you mining a cryptocurrency, essentially. And I will draw a picture of my cat on all of them. Wish you all luck. I don't think this marker works anymore. Nice. Good job including units. All right, I got 2 more. I think I need to look up the last one to make sure. And don't give up. Maybe somebody did it wrong as well. Somebody already wrote the answer. Let's see what it is. Go, go, go. Nice. There are multiple markers. Awesome. Was that all of them? Dun, dun, dun. Are we all confident that these are the answers? No. Any other takers? I'll give you 30 more seconds if anybody wants to challenge one of these answers. I know, let's see. Let's see who wins. 2 more seconds. You want to verify things. All right. Are you ready? Let's see who mined. Oh. I'll give you participation points if nobody else wrote an answer next to the number. Oh, nice. Let's see. Oh, we have a challenger. All right. Let's see. Let's see who wins. These are apparently the answers for the first two. And now I have to do math. So 1.26, I assume that is correct for the first one. So nice. Who wrote the answer to number 1? Awesome. You get. I just bought a big box of used discs, so you get somebody's old book from it was their school floppy disk. 1 Litecoin for you. Good job. And then for number 2, 385.07 atomic mass units. I don't think either of you got it. Or maybe you added it instead of multiplying it. So, all right. So if 385 is the answer, who's closer to it? The first one's 44. The second one's 32. All right. Who wrote the 44? All right. You get a driver installation disk. Good job. And then number 3, I just checked it. It was apparently 15 plus, according to Google, 15 plus 57, which is 72-ish, 73 rounded up. Perfect. So good job. You win a. Congratulations, everybody. So that is essentially what's going on inside of a computer when you're connected to the Bitcoin network. People are doing math problems. Computers are doing math problems very quickly, and just like whoever gets it first wins a little bit of Bitcoin. And so that's how the money keeps going. All right. So I hope that was fun. It's fun to do that every semester. I think that's all that I wanted to say about cryptocurrency. Are there any questions before I switch gears to a new set of slides? So yeah, that usually you're buying from somebody who wants to sell it to you. It's somebody else's account, and then they'll transfer it to you. Yeah, it's very hard. It's you have to get really lucky to mine it if you want it that way. It's very, very unlikely that you'll get it because there's so many computers trying to do it at the same time. Yeah. Any other questions? All right, but shoot, man, I should have bought it last year or when I started teaching. I don't know. It's a little high right now. It's just gambling though. So please don't do it yourself unless you understand the risks. All right, let's keep going. Let's talk about a new topic for the rest of today. I've got a set of slides on a fun little interdisciplinary topic, but it's a good segue after those slides about computer science and other disciplines because this is called game theory and it is used all over the place. All right, so I want to teach you a few aspects of this field of study called game theory, and you'll see the ideas that maybe you could program one day. All right, so this has to do with a lot of things. The game in game theory is very, very vague and generic. So you can use game theory for a lot of different purposes, including the silly example of people selling or in Fresno, so we're going to say corn. All right, so if you're a buyer and a seller, so game theory is used in economics in addition to plenty of other places. So I would like to teach it to you. So here's a silly example. We've got 2 corn producers. You got, I don't know, Fresno State and somebody else. 2 corn farms, and they're both going to try to compete for your money. All right. So you've got side of the road stand A selling corn, person A, and you got side of the road stand selling corn, person B. All right. And so let's see, A and B. If one person sells their corn at like a super high price and the other person sells their corn at a super low price, where can I put all this? Let's say like person A is like, I'm going to sell my corn for $50 an ear of corn, and the other person's like, I'm going to sell my corn for $5. Everybody's going to go to stand B, right? That's definitely how economics will play out, right? That makes a lot of sense. Everybody's going to go to the cheap one because corn is mostly corn. You can't really make designer corn, I would say. Okay, especially with that much of a markup. So the ideas of game theory will tell us that, all right, if this is equivalent corn, if person A wants to stay in business, they will drive their prices down. Their prices will be driven down to be the same price as the like the cheaper person, right? So this is going to go down to $5, essentially. That's what's going to happen, right? And so game theory is like a framework. It's a mathematical framework. It's going to tell us exactly, it's going to explain why that happens in real life, all right? So there will be what's called an equilibrium of prices. So that's a word we've seen in other places. This is a key idea for game theory, all right? So selling corn is apparently a game as far as game theory is concerned. And so this is what's going to happen unless they do something illegal, right? If the two sellers collude on the price, then there's a reason why you don't have laws, like laws prevent that. Like they can both be like, oh, you know what, we're both going to sell for $50, and that creates a different equilibrium, but an illegal equilibrium. Okay, so luckily there are laws against that, but that's why monopolies are a bad thing. Okay, so again, game theory is going to tell us what's going to happen and where the equilibrium will be. This is a relatively recent field of study. It's an offshoot of mathematics, I would say. It was invented by a mathematician named John Nash, who had a fun little movie, a little bit sad, but like interesting, fun movie still, called A Beautiful Mind, written about him. So consider watching that if you've never seen it before. It's a famous movie. And so he invented this idea of game theory, this field, all right? And I'd like to teach a little bit of it to you. It is very, very generic. So game theory works for computer science topics, it works for economics topics, and everything in between. So as far as game theory is concerned, a game is defined as a strategic interaction between individuals in situations. So that's super, super vague, right? It applies to pretty much anything you could ever want to do. So in addition to playing actual games, a game could just as easily be two corn producers. Two corn producers selling corn. That's their situation, right? So it can handle a lot of different things, which is good. Like that's why people like it and flock to it and learn about it. So yeah, it's useful in computer science as well. And there are two main kinds of games that game theory studies. There are cooperative games and non-cooperative games, all right? So that's more or less, their definitions are more or less what your intuition tells you. A cooperative game is when it makes sense to form groups and help each other, right? So a cooperative game is when people are better off working together, like coming up with a corn business or something, I don't know, or like making groups as you're playing a board game. Like cooperative games sometimes happen, and that's when people are better off working together and forming groups/alliances, right? That's what a cooperative game is for game theory. And a non-cooperative game is when it's impossible to form alliances. Like it doesn't work out ever. Or like if anybody in a non-cooperative game ends up working together, if the individuals end up ever working together, it's because they were threatened into doing it. All right, they didn't really want to, they were kind of forced to in a non-cooperative game. So people can still work together, but it's not a good thing. All right, so that's a non-cooperative game. All right, so in general, a cooperative game and the theory behind it, cooperative game theory, is all about like studying what it means to be fair and like what's going to happen when everything's nice and fair. And a non-cooperative game theory is all about like you're trying to win. What's the best way to win? Okay, so hopefully you will take away, if you ever become a politician, you'll use game theory, you'll use cooperative game theory rather than non-cooperative game theory. I don't know. So, all right. So it's used in so many different places, and there's a lot of computational power behind like solving for these equilibriums. So this is kind of why I want to teach it to you. It's used in a bunch of different things, which are maybe some things that you want to study later. It's used in econ, it's used in political science, it's used in biology even. Like game theory can explain what's going to happen in biology and how like populations of animals grows and shrinks and stuff like that. That's a game. Philosophy, and just like this is econ all over again. Like, but even if you're a corn producer, this is useful. Okay, so people, they like econ especially. People, they spend a lot of money and they write some programs that try to beat other people's programs to solve for the optimal strategy of playing their game, whatever that is. Maybe that's being on the stock market, buying Bitcoin, who knows? But game theory powers all of those things, and you can write algorithms that are better than other people's algorithms and make money. So this is kind of worth studying in that way. It ties it back to computer science, at least. And so I'd like to teach you an example of a non-cooperative game. It's called the prisoner's dilemma. Have any of us heard of that before? It's like the quintessential example of game theory when you're first learning it. So I want to give that to you first. There's a fun little YouTube video explaining it in more depth, but I will do my best to explain it in some slides. So this is an example of a non-cooperative game where the equilibrium, we're going to solve for it, and it's not going to make any sense. But game theory is going to tell us why it makes sense at the end. Right? It's going to be very, very counterintuitive, and so that's why it's a good example. Right? So here is a non-cooperative game, and we're going to study it. All right? So it's called the prisoner's dilemma, and so you've got two prisoners. Right? They've been both arrested and accused of committing some crime. Let's say that they stole something. I don't know. So you've got two prisoners, and they are put into two separate interrogation rooms. They're caught at the same place at the same time, and they think the police think that they've committed some crime. They're put into two separate rooms, and they're questioned. All right. They're given two options. They're each given two options. Yes, they're given the following options. And it depends on, like, do you want to confess right now to the crime, or do you not want to confess to the crime right now? All right, so here are your four possible outcomes, because each of them could either confess or not confess. You got four outcomes. And so here's what they say up front, the interrogation people. They say, all right, if prisoner A confesses, then they'll get 0 years in prison. But if prisoner B if prisoner A confesses and prisoner B does not confess, here's what's going to happen. Prisoner A is going to walk free, and we're going to put prisoner B away for lying for 10 years. Okay, so that's option one. If prisoner A confesses, but prisoner B does not confess to the crime, then prisoner A is going to walk free, prisoner B is going to get 10 years in prison. Okay. Outcome two is if prisoner A doesn't confess and prisoner B confesses, then it's going to be the flip of that, right? If prisoner A doesn't confess, then they're going to get 10 years if prisoner B confesses. Right, so it's really just, there's a grid that we can draw, and that makes more sense. Here are the options for each prisoner and what's going to happen. Prisoner A, what they do, and here's what prisoner B might do. So, oh wait, I need to draw that lower. So prisoner A, they could either confess or not confess. That's what I'll use to mean those things. And then prisoner B could either also confess or not confess. And so we just saw prisoner, this outcome was if prisoner A confesses but prisoner B does not confess, then what are their sentences? Prisoner A is going to walk free, prisoner B is going to get 10 years. And the flip of that is if prisoner A doesn't confess but prisoner B confesses, then prisoner B gets to walk free, 0 years, but prisoner A is going to spend 10 years in jail. Okay? Outcome three, if they both confess, if they're both like, yeah, okay, we got caught, we're both confessing, then they're each going to get 5 years. All right, 5, 5. A is going to get 5 years in prison, B is going to get 5 years in prison, which is better than 10. And then outcome four is if neither of them confess. If neither of them confess, all the evidence they have is circumstantial, and they will both walk free. Okay? They're both going to get 0 years in jail, and both of them know that. They know that this is the setup, this is what the interrogation people are telling each prisoner, but they're in separate rooms, they cannot talk to each other. Okay? What should they do? What do you guys think? What should these prisoners do? What's their optimal outcome?
What should they do? What do I think?
Good question. Yeah, answer both of those for me.
What they should do is go for the 0-0.
They should not confess.
My line of thinking is that my risk is, so
Yeah.
I think it's going to be 5-5.
Good, yeah. Does anybody agree, disagree with that? That's a great analysis. So, like, there's no question that this is the best outcome for the prisoners, right? If they could just both keep their mouths shut, they could both walk free. But the problem is going to be they're in separate rooms, right? So, like, just staring at the outcomes, this seems like the one that they should go and focus on, okay? But that's not going to be the case. We're going to notice that. So exactly what you said is going to turn up when we can mathematically define why, all right? So what we're searching for is an equilibrium, and the fancy term for it is it's called a Nash equilibrium. It's named after John Nash. And that's going to give us an optimal solution to this problem, to this prisoner's dilemma problem, right? And what a Nash equilibrium is the following. Let me read this, and then we'll talk about it. So a Nash equilibrium is when you find, it's like you write down a way to play the game. It's a bunch of strategies, one for each player. Like you, prisoner A, do this, you, prisoner B, do this. These are your strategies. That's what a Nash equilibrium is. It's a set of strategies, one for each player, that has the property that each player's choice is their best response to the choices of the other players. Like they could not do any better, even though it's a non-cooperative game, they have no control over anybody else. That's kind of what a Nash equilibrium is, okay? So what we're going to do, this is like a mathematical way, you can make this mathematical, of describing how to like play it safe. Because that's going to be the problem, right? It would be very nice for them to both do this. Just keep their mouths shut, and, oh no, why can't I draw? There it goes. For them to both just keep their mouths shut, and then they're going to walk away. But the issue is they're in two separate rooms. They cannot talk to each other. They don't know what the other is going to do. So because of that, like prisoner A does not know what prisoner B is going to say. So like they have to keep it, they have to play it safe, right? And that's what a Nash equilibrium is going to define. It's like a mathematical way of defining how to play it safe, all right? Another alternative definition for a Nash equilibrium is like this. It's a law that nobody would want to break, even if there was no punishment if you broke it. So a good example of a Nash equilibrium with that definition in mind is like a stoplight. We all obey our stoplights, right? If we see a red light, we don't go, right? Hopefully. But you could have gone, right? If you come up to a red light with your car, you could just plow through it, right? Most likely there is not a cop anywhere near you. You will get away with it. Why do we still stop at red lights? Yeah, because we want to live, right? We all have agreed as a society that we're going to stop at red lights because we value our lives. So that's what a Nash equilibrium is kind of about. That's like we want to play it safe, right? And so there's a way to mathematically specify that. It's like a self-enforcing law, essentially. And so for the prisoners, we would like to figure out, like, I cannot control what the other person can do. What's the best outcome for me? And it's going to involve taking averages of each possibility. All right, we're going to take some averages. Like, what's the average sentence in terms of what I can control? All right. And so let me draw that for us. All right. So we can talk about this problem through the lens of either prisoner because it's going to be a symmetric problem. So let's zoom in on prisoner A because you could solve this for prisoner B as well. It's going to be the same answer though. All right. So let's say that we're going to solve this problem from the perspective of prisoner A. What should prisoner A do? All right. Well, here's how you solve for a Nash equilibrium. Okay. What we're going to do is we're going to circle the two outcomes as far as prisoner A can control. All right. Prisoner A can either confess or not confess, right? And so either prisoner A, if they confess, they're in one of these two outcomes. And if prisoner A does not confess, they confess, they're in one of these two outcomes. And if prisoner A does not confess, they're in one of these two outcomes. Does that make sense? That's all prisoner A can control. They don't know which one they're going to get, but they know it's one of these two if they confess, and one of these two if they don't confess. Okay? And you could do the same thing for prisoner B. It's going to be symmetric. And so this is how you solve for the Nash equilibrium. You're going to be like, all right, from prisoner A's perspective, what are they going to do? Like if they can do the following. If they confess, what's going to happen? And if they don't confess, what's going to happen? Let's try all the possibilities. Cool. And what we're going to solve for is like, because they have no control, it's like equal 50-50 chance essentially which outcome they're going to get. So we're going to take the average. What is the average sentence for prisoner A if they confess? Well, 5, like if either B confessed or did not. If they confessed, they're getting 5. If they did not confess, but you did, prisoner A, you're getting 0 years in jail. And so they have no control over the 5 or the 0, which one they're going to get. So we're just going to take the average, right? So if prisoner A confesses, what is the average time they're going to spend in jail? All right, so that's going to be 5. For this case, it's 5 plus 0 over 2. So that's 2.5 years on average if they confess. 2.5. And then if they don't confess, what are their options? Well, if they don't confess, like they do have the option of spending 0 years in jail, which is nice. But if prisoner B does confess and they don't have control over that, they're getting 10 years. Right? So the average for that case, if they don't confess, is 10 plus 0 over 2, which is 5 years on average spent in jail. And that is why, even though if they could just keep their mouths shut, like they'll both walk free, but because this is a non-cooperative game, the equilibrium takes us to confessing, Does that make sense? It's very counterintuitive. Like, the best outcome is that they both just don't say anything, but neither of them are. They're both gonna confess because of this. They have no control over the person in the other room. They only have control over themselves, and they're gonna do the best thing on average. Right? They're gonna find the best possibility because they're not sure which of these outcomes they're gonna get. So you're just gonna they're gonna average over all the possible universes, and they're gonna find the best one that works for them. Okay. So that's the secret. So in the average case, it always makes the most sense for each prisoner to confess. So the equilibrium is going to go to here. Both prisoners will probably end up confessing, even though there's a better outcome right here. See that? There's totally a better outcome. And so that's how we solve for it. It seems like a paradox. Seems paradoxical, but game theory gave us a way of explaining it. And so that's what you can do for even more complicated problems. Okay, so that's the prisoner's dilemma. That's a good example of a non-cooperative game and how to solve for the right outcome. What's going to happen? Any questions about that? A fun little idea, I think. Fun little example, and I think that's what I wanted to stop with. So we're just in between slides. We started these guys. There's more to talk about for game theory, but we'll just deal with that next non-programming lecture. And I think that's all that I wanted to say today. I will talk about our final, because our final exam is coming up. Let me just say this now. We are in week 15, so there are 17 weeks of classes. We have class through week 17, and then week 18 is finals week, and we have some scheduled final. I forget what day it is, but we'll look it up together on the syllabus on Wednesday and talk about it then. Okay? So yeah, that's all that I've got for the day for us then.